Okay, in section 6.6, we're going to talk about what are called quantum numbers. Now, we've already looked at quantum numbers in terms of the Bohr model, right? The Bohr model said that the energy of the electron in the hydrogen atom, the electronic energy, was related to this quantum number n. Whole numbers, counting numbers from 1 to infinity. That's a quantum number. But it turns out that Bohr's model was limited in terms of its scope. It could only accurately describe the hydrogen atom, the helium-1 ion, the lithium-2 ion, the beryllium-3 ion, and so forth. It could only accurately describe the energy levels of species that had one electron. So hydrogen atom has one electron, the helium ion has one electron as well. Beyond that, even the simple helium atom with 2 electrons, the Bohr model failed to be able to accurately determine the energy levels of the electrons. So it was left to other physicists to figure out the solution. And one solution is what's called the Schrödinger equation. Schrödinger essentially modeled the atom as a wave. In particular, what we would call standing waves, just like de Broglie, or at least related to what de Broglie came. And Schrödinger went further than de Broglie. He actually went through and figured out the relationship behind this wave, which will use the symbol psi to represent what's called a wave function. It's a mathematical equation that describes the electron as a wave. And it depends on all 3 positional components, and it also depends on time. So we're not going to go into the details of the mathematics behind the wave function in this course because it requires some pretty hefty mathematics that we don't have time to go through. So we'll just leave the description of the Schrödinger equation at that. It is a mathematical equation which describes the wave-like behavior of the electron in an atom. However, one of the results of the Schrödinger equation is that when we solve the equation, we end up with a set of quantum numbers. More than one. The first one is n, which has got a name. It's called the principal quantum number. And in a sense, it describes 2 things. Primarily, it describes the energy of the electron. Okay? But because the energy of the electron is related to how far it is from the nucleus, its distance to the nucleus, because remember, the interaction, the energy that we're talking about is it's electronic. The charge of the electron, the negative charge of the electron, is attracted to the positive charge of the nucleus. So it's also related to the distance of the electron from the nucleus. And it turns out n takes on the same values that it did in the Bohr model. Okay, 1, 2, 3, 4, 5, 6. So the reason that Bohr, we believe now, the reason that Bohr's model worked for hydrogen was that because it was such a simple system, the wave mechanics of an electron mathematically superimposed with his model. And so he had this value n, this quantum number, which now we realize is really the energy of the electron. So the further the electron is from the nucleus, the more energy the electron has. Now remember, the electron, as we ended our previous lecture, we don't think of it anymore as a particle moving around the nucleus. We think of it as a wave that is spread out around the nucleus with a probability distribution. Okay, so we'll get more into that when we talk about atomic orbitals. Okay, so there's our first quantum number n. The second one, the symbol for this is an L. Just so we don't confuse it with a 1, I'll use a cursive L. This is called the angular momentum quantum number. And the angular momentum quantum number describes the amount of angular momentum. Remember, the electron it has some sort of motion going on, so there's some sort of angular momentum it has, or at least it behaves as though, in some sense, it's moving. So it has angular momentum. In a sense, really what the angular momentum quantum number is telling us, one interpretation, is it is telling us the shape of the electron distribution. And that electron distribution, we'll call it an orbital. I'm being a little bit loose with my terminology here because we can mix terms together and it gets difficult to define things perfectly at this stage. So the angular momentum quantum number can be 0, or it can be 1, or it can be 2, or it can be 3, but it can never be as large as n. So its maximum value, the maximum it can be, is n minus 1. So it can be less than n. So for example, if n is 3, L could be 0, that's less than n, or it could be 1, that's less than 1, or it could be 2, that's less than 3, less than n, right? So anything less than n, starting at 0. Okay, this essentially gives us the distribution of how the electron is spatially related to the nucleus. Okay, it's an interesting quantum number. It's an important one for us in chemistry. We'll talk more about it when we get into the atomic orbital discussion. For right now, all we're doing is we're looking at these numbers. In the next section, we'll look at how they affect the actual atomic orbitals. The third quantum number is m sub L, and this is called the magnetic quantum number. It actually has a couple different names, but I'm going to call it the magnetic quantum number because one of the other names is very difficult to pronounce, so I won't even worry about it. Okay? This gives us the direction of the electron distribution, which way it's pointing. Again, of this, what we would call an orbital, which we'll look at it in great detail in the next section. So these are the three quantum numbers. Now, one way to think about this is that, let me make a little more space here. If you imagine that you were trying to compute the direction of a trajectory of some sort of classical particle. So this is 3 dimensions, right? And imagine you're trying to figure out the path of this ball. So it's, maybe doing something like this, right? Okay? It's undergoing some sort of motion. In order to properly determine where that ball is and which direction it's moving, you need 3 values, right? You need x, you need y, and you need z. You need 3 dimensions. So we need to know where it is on the x dimension, on the x-axis, the y-axis, and the z-axis. So we need 3 values, right, to identify the trajectory of that ball, because we live in 3-dimensional space. Well, in a sense, quantum mechanics is a different type of physics. than classical mechanics, but it still has similar rules. And one of the rules it has is that to determine the wave, to determine the properties of the wave that we're talking about, this electron, it is in three dimensions, three-dimensional space, so it also needs three values. And these three values are what? They're n, L, and m sub L. Okay? So one way to think about this also would be to say, well, wait a minute, what if I just had a string on a guitar? Right? We talked about that in an earlier section. If you pluck the string and it starts vibrating, you only need one quantum number. You just need n. What if you had two dimensions? Is there a musical instrument that has a vibration in two dimensions? And you know the answer to that. What musical instrument has a vibration in two dimensions? It's a drum, right? A drum is a flat surface, so it vibrates in two directions. So it turns out the drum, if you solve the mathematics of the drum, you get two quantum numbers because it is two-dimensional. Now, the atom is a three-dimensional object. The electron is outside the nucleus. It's free to do whatever it's going to do, the physics of whatever the electron does. It's going to do it in three dimensions. So for that reason, we have three quantum numbers. N, which gives us the energy of the electron, just like it did in the Bohr model. L, which gives us the amount of angular momentum, something about the way the orbit of this electron is distributed in space. And then m sub L, what direction that electron distribution is taking in space. Okay? So three quantum numbers, n, L, and m sub L. Now, here in table 6.2 are some rules or something about the numbers. We're going up to n equals 4. This only goes up to n equals 4. On occasion, we go higher than 4, but this is good for instructional purposes. Some of the heavier elements in the periodic table, we would want to have n greater than 4. So what this says is that if n is 1, L has to be less than 1, but still be a whole number, and it can't be negative. So if n is 1, the only possible value is 0. Oh, I didn't actually tell you when it comes to m sub L what the rule of m sub L is. I described the orbital, but I did not actually go through and tell you what the numerical values of m sub L are. So let me show you what that is. Oops, okay. I see. We'll just do it down here, okay? There we go. Okay, so m sub L can be 0, plus or minus 1, plus or minus 2, plus or minus 3, all the way up to plus or minus L. Meaning that if L is 0, m sub L is limited to 0. But if L is 1, m sub L could be 0 or plus 1 or minus 1. Okay? So in other words, 0 is always a possibility, but you can increase the possibilities by increasing L. So in this table 6.2, it says that if n is 1, L has to be 0 because L has to be less than n, but no less than 0. So 0 is the only possibility. M sub L is limited by L. M sub L can only be as high as plus L and as low as minus L. Notice it can be negative, right? So m sub L, if L is 0, has got to be 0 also. If n is 2, then L now can be 0 or 1 because 0 is less than 2 and 1 is less than 2. If L is 0, M sub L is 0, as we just discussed. But now, because L could be 1, if L is 1, M sub L could be minus 1, 0, or plus 1. Plus or minus L and 0. 0 is always an option. If N goes up to 3, then L can be 0, 1, or 2. All three of those values are less than 3, right? Can't be 3, though. And then there's 3 possibilities for L, so we're going to have 3 ranges for M sub L. If L is 0, M sub L is 0. If L is 1, M sub L is minus 1, 0, or plus 1. And if L is 2, M sub L is minus 2, minus 1, 0, plus 1, or plus 2. So notice what happens. As L increases, as L increases, the possibilities for M sub L increase. So if you go all the way up to L equals 3, M sub L goes from minus 3 all the way up to plus 3. That's 7 different possibilities. So those are plotted in the diagram below here. It's a very interesting little diagram, right? What it's showing you are for the different values of n. So on the left, n equals 1, L has to be 0. For n equals 2, just to the right, you've got 3 possibilities for L, minus 1, 0, and plus 1. For n equals 3, you could have L equals 0, or you could have L equals 1, or you could have L equals 2, and all the M sub L values are shown there, all the way up to n equals 4. So that little table at the top is represented using these little box diagrams. These little box diagrams are not a bad way to represent it. We'll see it when we start looking at electron configurations, that these boxes are a good way to represent atomic orbitals. Okay? Now, there's some terminology here. One terminology is that for any set of quantum numbers where n equals 1, we're going to call that the n equals 1 shell. For any of these boxes or any of these quantum sets of quantum numbers, if n equals 2, we're going to call that the n equals 2 shell. And for all of the boxes, so in the middle there where n equals 3, you've got 1, 3, and 5, so that's a total of 9 boxes. All of those boxes together, or all of those combinations of quantum numbers, that's called a shell, and it would be the n equals 3 shell. And then you can go all the way to the 4 shell. Now, within a particular shell are what we call subshells. So in the n equals 1 shell, there's only one subshell, and that's called the S subshell. So let me give you, I'm going to actually see if I can put this in as a little box here. Oops. Okay, so maybe I can write here. If we're talking about L equals 0, I guess for some reason it's just not working. Let's do it over here. If we're talking about L equals 0, we're going to call that a subshell, and we're going to call it the S subshell. And if L equals 1, we're going to call that a P subshell. If L equals 2, we're going to call it a D subshell. And if L equals 3, we're going to call it an F subshell. Okay? So if you take a look at this diagram, go all the way up to n equals 4, all the way to the right, n equals 4. There are 4 separate subshells there. There's the L equals 0 subshell, which is called an S subshell. It has 1 box. So we're looking all the way at the right. The second one up is L equals 1. That would be called a P subshell. There are 3 boxes in that subshell. Go up one more, L equals 2. That would be called a D subshell. There are 5 boxes there. And then the one at the top, on the right again, L equals 3. There are 7 boxes there. That would be called an F subshell. Okay? So subshells are all of these combinations that have the same value of L within a shell. Okay? That's the idea, essentially. Now, let's come back to one more quantum number that we have to consider, and that is called the magnetic spin. As physicists started studying the electron and its behavior within atoms in great detail, one of the things that they could not account for was the fact that there appeared to be two possible states of the electron. And we now know that this is a fundamental inherent property of the electron. The electron comes under the category of what we call fermions, and fermions have a property called spin. And spin is an inherent property of the particle. And it's just something that it has. Just like a cat has 4 legs, an electron has spin. Okay? Just like a proton has mass, a proton also has spin. So what is this spin? It's a little difficult to figure out in our understanding of the macroscopic world what this subatomic property is called spin, but we'll give it a shot. Okay? The electron, one type of experiment we can work on is this one here depicted right here at the bottom. Essentially what you do is you take an oven with atoms in it, and the atoms have an odd number of electrons. So you wouldn't do this with calcium because calcium has 20 electrons. It has an even number of electrons, no good. But you might do it with potassium. Potassium has 39 electrons. That's an odd number, so that could work. You could do it with gold. Gold has 79 electrons. Silver has 47. Odd numbers, right? Essentially what happens is this magnetic spin under normal conditions is a random phenomenon, meaning that if you have a group of atoms, the electrons in those atoms will be spinning one direction or another. Okay? So imagine, for now, that the electron is spinning on its axis. And it could spin one way, or it could spin the other, the opposite. That's about as close as of a physical analogy as we can come in describing this magnetic spin. It turns out the electron is not spinning in the way that we think of something as spinning, but it behaves as though it were. So that picture at the top, that's showing the electrons spinning on their axes in opposite directions. One's going clockwise, the other one's going counterclockwise. I'm going to point out now that this is an analogy. It's not factual. They do not spin on their axes, but they behave as though they were classical particles that do. Okay? And this phenomenon is random, meaning that if you had a large number of electrons, 50% of them would be spinning one way, and the other 50% would be spinning the opposite. So what happens then is if you have an odd number of electrons, so let's say you've got 47, this is silver, 47 electrons. What you would expect is 23 electrons are spinning one way, maybe this way, and another 23 are spinning the opposite. But you got one more electron, right? That's 46, you got one more. So where's that one electron? What's it doing? Well, it could be spinning either way. It could be going this way, or it could be going that way. So what you do is you shoot these atoms one at a time through this slit screen, which is in blue, put it through a magnetic field. So notice there's a magnet in between the path of the slit and a detecting screen. And when one atom flies through, there's a 50-50 chance that this one electron here is spinning either this way or that way. So let's say it's spinning this way. Perhaps the electron is deflected by the magnetic field. The magnetic field causes it to bend, to change its path. It accelerates the electron either upward or downward. And what you find is that half of the atoms, so you just keep shooting one atom after another, half of them go this way, the other half go this way, down or up. And so we might call these electrons that went up spin up. And the ones that went down, we call them spin down. Okay? Now, the reason it's random is because this magnetic spin in the absence of a field is pretty random. So that big group of atoms that's over here in the heater, in the oven, the 47th electron in those atoms, half of them are going one way, the other half are going the other way. So half the atoms go up and the other half of the atoms go down. And so there are two possible spin values. And so what we're going to do is we're going to claim that there's a quantum number associated with that. And it's either plus a half or a minus a half, meaning that the electrons in these atoms have a spin of plus a half or minus a half. If the spin is plus a half, we call it spin up, and we're going to represent it with an arrow pointing upward. If the magnetic spin quantum number, m sub s, is negative a half, we're going to call it spin down, and we're going to represent it with an arrow pointing downward. We'll use this notation of the arrow for the electron. So this arrow represents the electron. And we're going to say the electron, so we're not using a little ball to represent them here. We're using an arrow to represent them. So if the arrow points up, it's a spin up. If the arrow points down, it's a spin down electron, which tells us the magnetic spin quantum number of the electron that we're looking at. Okay? So 4 quantum numbers, 3 of them are the inherent properties of where the electron is in relation to the nucleus. So that's n, l, and m sub l. The 4th one is an inherent property of the electron itself, independent of what orbital it's in.